How do you support a rotating shaft? It sounds like one of the simplest problems in mechanical engineering. Take a shaft, hold it in place, allow it to rotate. Problem solved. Except it isn't. That same question has produced some of the most sophisticated components ever developed, because every machine asks it under different conditions. What if the shaft spins at 30,000 revolutions per minute? What if it carries several tons? What if there's almost no space available? What if friction becomes unacceptable? What if contact itself becomes the problem? Every answer produced a different type of bearing, and every bearing represents a different engineering compromise. Understanding bearings is about understanding which problem each geometry was invented to solve. Let's start with the simplest question. How do you support a rotating shaft while losing as little energy as possible? The obvious solution would be to let the shaft slide inside a hole, but sliding surfaces generate enormous friction. Every revolution wastes energy as heat while continuously wearing away both surfaces. Engineers solved this centuries ago by replacing sliding with rolling. Instead of allowing the shaft to slide, hardened steel balls roll between two precisely machined raceways. Rolling friction is orders of magnitude lower than sliding friction, allowing machines to spin faster, consume less power, and last dramatically longer. That sounds like the perfect solution. But every engineering solution creates a new constraint. A ball only touches the raceway over an incredibly small area. Imagine balancing the weight of an entire car on 8 pencil tips. That's surprisingly close to what's happening inside many ball bearings. Nearly the entire load of the machine passes through microscopic contact patches only fractions of a millimeter across. Those tiny contact areas produce enormous Hertzian contact stresses. The steel survives only because both the balls and raceways are hardened to exceptional strength, while a microscopic oil film prevents direct metal-to-metal contact. Even then, fatigue eventually wins. Microscopic cracks form beneath the surface before slowly growing outward until pieces of the raceway begin breaking away, a failure known as spalling. Ball bearings therefore occupy a very specific place in engineering. Whenever rotational speed matters more than maximum load capacity, they remain the preferred solution. Electric motors, machine tools, cooling fans, robotics. Almost every high-speed rotating machine begins with the same answer: use balls, until that answer is no longer good enough. So what happens when the load becomes too large for a ball bearing? This is exactly the problem engineers encountered in heavy industry: steel mills, mining equipment, railway axles, industrial gearboxes. The contact stresses inside ball bearings eventually become too high. The obvious solution isn't stronger steel, it's changing the geometry. Replace each ball with a cylinder. Instead of touching the raceway at a single point, a cylindrical roller contacts it along an entire line. Nothing else changes, the bearing still rolls, the shaft still rotates, but the same load is now distributed over a much larger contact area. Contact stress drops dramatically, load capacity increases dramatically. One simple geometric change fundamentally alters the bearing's capabilities. But once again, the new solution introduces a different problem. Long rollers don't tolerate misalignment well. If the shaft tilts even slightly, the load shifts toward one end of the roller. Instead of distributing force evenly, the bearing develops concentrated edge loading. Local stresses increase rapidly, fatigue accelerates, and bearing life falls. Roller bearings also generate more internal sliding than many engineers realize. At high speed and light load, the rollers can skew slightly out of alignment with the raceway, and the cage itself can begin to slip rather than track the roller set exactly. That skew and slip translate directly into friction. That extra friction becomes heat. Large industrial roller bearings therefore require carefully engineered lubrication systems, not simply to reduce friction, but to remove heat before it destroys the lubricant itself. Whenever enormous radial loads dominate the design, engineers willingly accept those trade-offs, because the alternative is a ball bearing that simply cannot carry the load. But another question soon appeared. What if the load isn't purely radial anymore? A truck wheel doesn't just support the weight of the vehicle. It also experiences side loads while cornering, braking forces, acceleration, road impacts. The forces constantly change direction. A conventional roller bearing handles radial loads beautifully. Axial loads are another story. So engineers asked a different question. How do you support a rotating shaft when the forces come from every direction? The answer was to reshape the rollers. Instead of cylinders, they became cones. The raceways became tapered as well. If you extend every tapered surface inward, they all intersect at a single point along the shaft's center line. That geometry is remarkably elegant. Every roller now rolls naturally along its raceway while simultaneously carrying both radial and axial forces. The bearing no longer fights axial loads, it expects them. But tapered bearings introduce a challenge that earlier bearings largely avoided. They require preload. If there's too much internal clearance, the rollers move before carrying load. The shaft loses stiffness. Every change in load direction produces impact. Too much preload creates the opposite problem. Internal friction rises sharply. Operating temperatures increase. Lubricant ages faster. Fatigue life decreases. Somewhere between those two extremes exists a narrow operating window where stiffness, efficiency, and durability all coexist. This is why wheel bearings are assembled to extremely precise torque specifications. The preload is one of the bearing's most important design parameters. Tapered roller bearings became the standard solution wherever engineers needed stiffness under complex loading. Truck axles, construction equipment, automotive differentials, industrial gearboxes. But even this elegant solution couldn't solve every problem. Sometimes the limitation wasn't the load, it was the available space. What happens when there isn't enough room for a ball bearing at all? Modern automatic transmissions contain dozens of rotating components packed into an astonishingly small volume. Planetary gear sets often leave only a few millimeters for an entire bearing assembly. Balls simply don't fit. Engineers solved this problem by abandoning the idea that rolling elements need to be roughly spherical. Instead, they made them extremely long and extremely thin. Needle bearings use slender cylindrical rollers whose diameter is only a fraction of their length. The result is remarkable. They provide line contact, similar to conventional roller bearings, while occupying only a tiny radial cross-section. Few bearing designs achieve more load capacity from less space. But geometry always demands payment. Because the rollers are so long, they become highly sensitive to shaft deflection. Even slight bending concentrates force along only part of each roller instead of distributing it evenly. Contamination becomes another serious concern. A particle that might pass harmlessly through a ball bearing can produce severe local stress concentrations inside a needle bearing. Many designs eliminate the inner race entirely. The rollers run directly on the shaft itself. That saves even more space. But now the shaft must also function as a precision bearing surface. Its hardness, surface finish, roundness, heat treatment. None of those properties are optional anymore. The shaft has become part of the bearing. Needle bearings reveal one of the deepest principles in engineering. Every optimization moves the problem somewhere else. You save space, but you demand greater manufacturing precision. You reduce package size, but you increase sensitivity to contamination and alignment. 4 bearing types, 4 different answers to the same question. Point contact for speed, line contact for load. Conical geometry for forces that come from every direction. Needle geometry for spaces where nothing else fits. But notice what all 4 have in common. Every single one of them solves the problem the same fundamental way. Take something round, put it between two surfaces, and let it roll. That assumption is about to break down, because there's an entire category of problems where rolling elements, no matter how you shape them, start to struggle. What happens when the load stops pushing sideways against the shaft and starts pushing straight through it? What happens when the bearing has to support hundreds of tons at a time, or spin with no lubricant at all, or hold a position so precisely that a single ball bearing would ruin the machine around it? Those problems need a different idea entirely. That's where the next video picks up. 4 more bearings, including one that doesn't touch the shaft at all. If you want to understand machines at that level, subscribe to Engineering Manual, and we'll see you in part 2.